Chapter 10, the t-test for two independent samples, Part 3. In this video, I'll walk you through example 10.4, which uses data from example 10.1, but tests for a one-tailed hypothesis. So the research dealt with the effects of watching Sesame Street as a child on academic performance. So in example 10.1, we tested that hypothesis using a non-directional test, and we concluded that the t-statistic was significant. So with a one-tailed test, we're going to assess if we see the same results, and we should recognize that a one-tailed test is easier to pass, so we shouldn't be surprised by rejecting the null in this example. Nonetheless, it's important to walk through the steps, the 4 steps of a hypothesis test using a one-tailed process, so that you can see how the notation differs than a two-tailed or non-directional test. So before we begin, let's review some of the elements that pertain to a one-tailed hypothesis test. First, we use directional test only when predicting a specific direction of the difference is justified. In other words, the majority of hypothesis testing is done at the non-directional two-tailed test, and the reason for that is because a two-tailed test is more stringent, more difficult to pass. So we want to start at that level, and then if we have supporting evidence or literature that indicates a direction of this difference, then we would continue with a revised hypothesis at the one-tailed test. Again, one-tailed tests are easier to pass because the alpha levels are set closer to the center of the distribution. So following the steps, we would locate the critical region in the appropriate tail, meaning that if you hypothesize that the difference, right, in this case, the academic performance would be higher, then we're going to focus on this tail of the distribution. If we were testing the effects of an antidepressant drug, we would hope that the levels of depression would decrease. So again, different from what we have done in the past with a non-directional hypothesis, we had two tails, right, and we had the critical region defined on both sides of the distribution. For one-tailed, we have to be conscientious of what side we expect that mean difference to reside. Again, in this case, if we take the sample 1 minus sample 2, and we expect those who watch Sesame Street to have higher academic performance compared to those who didn't, then we would focus on a positive critical t-value. If the mean difference was looking at the effects of reducing depression with an antidepressant drug, then we would focus on the negative t-value or critical t-value. And then finally, we report use of one-tailed tests explicitly in the research report. So following our probability statement, given that, for example, we reject the null hypothesis, our probability would say p is less than alpha. If we fail to reject, it would indicate p is greater than alpha. Following that statement, we would include the phrase one-tailed test to signify to the consumer of our research that we did perform a one-tailed test using that specific alpha level. And that's important because, again, the one-tailed tests are easier to pass, so the consumer of your research should know that information. So here is the information that pertains to the research of a one-tailed hypothesis relating to the academic performance of children who watch Sesame Street as young children versus the academic performance of individuals or high school students that did not watch Sesame Street as children. So the null hypothesis stated here indicates academic performance of high school students that watch Sesame Street as children will be lower than or equal to the academic performance of high school students that did not watch Sesame Street as children. Again, the null says nothing is happening, no difference, no change. But when it's one-tailed, it also includes this direction. So equal to means no change. The direction that indicates lower is signifying that it would be opposite of what we are hypothesizing. Again, the research or the alternative hypothesis, I'll read in just a minute, indicates that we expect it to be higher. Their academic performance will be higher due to the fact that they watch educational television as children. So the notation that goes along with the null looks like this. So the null states that the average score for those who watch Sesame Street will be lower than or equal to the average academic performance score for those that did not watch. So no Sesame Street. So again, it's less than or equal to, or it could be written in this way. We could say the mu of Sesame Street watchers minus the mu of those that did not know Sesame Street is less than or equal to 0. So if we take this mean and subtract that mean, first we would anticipate it is equal to 0 because there's no difference. They're the same. And then we account for this verbiage lower. We would expect it to be lower. If it's lower than 0, meaning it would be a negative, we're saying that the academic performance average score of those who watch Sesame Street is less than the mean of the academic performance who did not watch. So hopefully that makes sense. If it's less than 0, it would be negative, meaning this value here is less than this second value. The alternative or research hypothesis would be stated in this form. Academic performance of high school students that watch Sesame Street as children will be higher, again directional, higher than the academic performance of high school students that did not watch Sesame Street as children. So the notation would be like this. So the average score of those who watched will be higher than those who do not watch or did not watch. Again, it doesn't include the equal because the equal is reserved for the null. So the research or alternative is strictly indicating the direction that we expect. In this case, we expect those who watch Sesame Street to have higher academic performance than those who did not. Or we could have it written in this fashion. So the mean of those who watched minus the average of those who did not watch is greater than 0, right? If it's greater than 0, then we're saying this number is higher, right? So, let's just make up numbers. 100 minus 80, right, would be something greater than 0. If this one's lower, the first one is lower than the second one, then it would produce something less than 0, a negative number. So again, this is how we would state the research and null hypothesis and include the proper notation to conclude step 1 of our hypothesis test. Step 2 requires that we set the criteria or the critical region for our hypothesis test. And to do so, we're going to need the degrees of freedom. So I just included the original data for this research so that we can see what the sample sizes were for each group. So again, they're independent samples, 2 different groups of individuals, and in fact, it's a quasi-independent variable because I cannot randomly assign individuals to one group or the other. They either did watch it, Sesame Street as children, or they did not. So they would self-allocate themselves into these different conditions or categories. And so N1 is equal to 10. We have 10 participants, and N2 is equal to 10. So the combined degrees of freedom is simply taking N1 minus 1 added to N2 minus 1. So we get 10 minus 1 is 9 plus 9 is equal to 18, and we had gone through that in example 10.1. We also need what alpha is set at, so we were instructed to conduct a hypothesis test, a directional or one-tailed test, and alpha equal to 0.01. And so now we're going to use that information, degrees of freedom with alpha level, and the fact that we're conducting a one-tailed test to find the critical t. So critical t. And again, because we are anticipating that this group, those who watched, will have a higher mean, the critical t will be a positive, and we will focus on the right side of the distribution. Again, here in the center, mu1 minus mu2 comes from the null and says that the mean difference is equal to 0. Now we're going to identify what the critical t value is given our t-table. So here's our t-table. Again, we're conducting a one-tailed test, so we're going to focus on this tier. Alpha is set at 0.01. Degrees of freedom is equal to 18, so we're just going to see where these things intersect with one another. And we find that our critical t is positive 2.552. So we set our critical region at positive 2.552. Again, we don't report it as positive negative because it's one-tailed, and we're calculating our t based on the hypothesis that the first distribution will yield a higher sample mean than the second distribution. Step 3 is to calculate the data in our collect our data and calculate the t-statistic. So again, this is to the left here in this data box. We have the information collected. We have our x values, the sample size, the mean, and sum of squared deviation. So I'm not going to go through how we produced all of those because that was in the previous video. Instead, we'll begin with our T-statistic equation, which we had already calculated, but just for review. And the equation for our t is our sample mean from our first distribution minus the sample mean for our second. That mean difference minus the anticipated population mean difference coming from the null, which is always equal to 0, over the standard error, in this case the estimated standard error of the mean difference. So let's replace variables that we already know. We know the mean of our first distribution is 93, minus the second was 85. I'm just going to move all of that over just a little bit. Minus 0, right? This is always representative of the null. There's no population mean difference over the estimated standard error of the mean difference. So our equation for the estimated standard error of the mean difference is as follows. We take the square root of our pooled variance over sample size 1 added to the pooled variance over sample size 2. We take those two fractions, add them together, and then take the square root. And our pooled variance, again, was calculated in the previous example. But again, just for sake of review and more exposure to the equations, our pooled variance, since we have the data right here in our table, our pooled variance is equal to sum of squared deviations for our first distribution added to the sum of squared deviations for our second over degrees of freedom for both distributions. So we have 200 plus 160 over degrees of freedom, 9 plus 9, and that gave us 360 over 18, and we have pooled variance equal to 20. Again, we had gone through all of these equations in example 10.1 in a previous video. So we can replace those variables here in this equation. So it's 20 over 10 plus 20 over 10. Again, focusing on the fact that these are separate fractions, and here in our pooled variance equation it's one fraction. It's the sum of two values over the sum of two other values. Just want to re-emphasize that so you don't make that mathematical error, which is very common. And 20 over 10 gives us 2 plus 2, which gives us 4, and our final estimated standard error of the mean difference is equal to 2 in this example. So 93 minus 85 was a mean difference of 8 divided by our estimated standard error of the mean difference of 2, and we get a t-value equal to 4. Again, we had gone through all of these calculations in example 10.1, but for the sake of greater exposure and walking you through the steps again, I thought it was important to revisit the calculations that enabled us to produce our t-statistic. And now, given our new t-statistic, that which you recognize has not changed, none of those variables had differed in the case of testing a one-tailed test. So what we need to do now, what has changed, is the critical region t-value. So now that we have our t, we're going to compare it to our critical t and then draw our conclusion. So to draw our conclusions, we're going to compare our critical t to our t-statistic. Again, here I've written in the center mu1 minus mu2. The null states that there would be no difference between those population averages. And we set our criteria at 2.552, which was based on alpha equal to 0.01, one-tailed test, and degrees of freedom equal to 18. And now we see where this value resides. Obviously, it's to the right of our critical t. We're happy, right? We get to reject our null hypothesis. And it should be no surprise that we are rejecting the null hypothesis because of the fact that we rejected at a non-directional, using a non-directional hypothesis test. Again, the critical t for a one-tailed test is going to be closer to the center. It's going to be a smaller value, which again makes it easier to pass the test. And one may wonder, then why do this? But obviously the data that we used was the same data for the two-tailed test. If you create new research, you're going to have a new set of data points, a new group of individuals and X values for each of your groups. But for purposes of simplicity, we're using the same data in that was used in 10.1, which is a non-directional test. So again, it should be no surprise that we reject the null. We're happy, and now we are going to write our concluding statement and include this new component of identifying that we conducted a one-tailed test. So step 4 requires that we draw conclusions. We make our decision regarding the null hypothesis. In this case, we reject the null. Results indicate that the academic performance of high school students that did watch Sesame Street as children was significantly higher than the academic performance of high school students that did not watch Sesame Street as children. We cite our test statistic, t, with degrees of freedom in parentheses of 18 is equal to 4.00. P is less than 0.01, which means that the probability of obtaining the sample mean that we did has less than a 1% chance of occurring if the null is true. Again, there's less than a 1% chance that we would obtain the sample mean difference that we did if the null were true. Again, the null says there's no difference. So again, it's less than a 1% chance that we would obtain a sample mean difference in the tail on the side of the distribution that we were focused on. And then we would include this new information which states that we conducted a one-tailed test. The measures of effect for one-tailed test for this particular example would not change because, again, let's just review the equations for our estimated d, r squared, and confidence interval. So d is equal to the mean of our first distribution minus the mean of our second over the square root of our pooled variance. Again, none of those values or variables change given the fact that we were conducting a one-tailed test. So our estimated D would not change. R squared, our equation, is T squared over T squared plus degrees of freedom. Again, the fact that we conducted a one-tailed test does not change any of those variables. And then our confidence interval equation is the mean difference is what we're calculating, is equal to the sample mean difference plus or minus our t-value from our table and coming from the percentage of confidence that we're implementing, multiplied by the estimated standard error. I'm going to give myself a little bit more room here. So their t-value, again, coming from the percentage of confidence and multiplied by the estimated standard error of the mean difference. Again, this t-value is not not the t-statistic. Again, it's based on the percentage of confidence that we're going to calculate and the degrees of freedom. So keep that in mind. And also something very important here, we conducted a one-tailed test hypothesis here, but the process of computing the confidence interval is always a two-tailed test process, or two-tailed process, I should say, because we're going to use the sample mean data as the center of our prediction and then calculate a range, right? A range from a lower value to a higher value. And again, so that encompasses two tails. So regardless if you conduct a one-tailed or two-tailed test, the computation or calculation for a confidence interval is always the process of using two tails, or the second tier in our t-distribution. And that concludes this illustration of a one-tailed hypothesis test using t-tests for two independent samples. Again, they're independent because of the fact that we have different participants in each category. Each sample represents two different populations. In this case, sample 1 represents population 1, which are those who watch Sesame Street as children, and sample 2 is representative of population 2, which is an illustration of the population of children that did not watch Sesame Street. And we're comparing their academic performance to see if there's a difference based on this different quasi-independent variable of watching Sesame Street as children versus not watching Sesame Street as children.